Hello, my name is Valeri Frumkin, and in this talk I'll be telling you about a new approach to fabricating optical components, which we call fluidic shaping. Currently, lenses and other optical components are fabricated by mechanical processes such as grinding, machining, and finally polishing, which is the most complicated part. These are complex processes that suffer from many drawbacks, but most and foremost, they require expensive and specialized equipment. Therefore, they are not well suited for rapid prototyping of optics. Now, whenever someone mentions rapid prototyping, the first technology that comes to mind is 3D printing. The problem is that the surface quality of 3D printed components is typically on the order of microns, much below that which is needed for optical applications. It is possible to improve the surface quality of printed components by various post-processes, but that again increases the complexity and the cost of fabrication. Another drawback of 3D printing technologies is that printing time is proportional to the volume. Therefore, printing large components or a large number of small components can take an unreasonable amount of time. Our motivation comes from the world of droplets, which are natural lenses with various optical properties depending on the liquid they are made of. In addition, due to the natural smoothness of fluidic interfaces, droplets have excellent surface quality. However, there are two major obstacles that we need to overcome if we are to make lenses out of droplets. The first one is obviously gravity. The effect of gravity on droplets can be characterized by a length parameter called the capillary length. It represents the relative importance of surface tension to gravity in a fluidic system. Here gamma is surface tension, rho is liquid's density, and g is Earth's gravity. Droplets with diameters smaller than their capillary length will remain spherical due to the dominant effect of surface tension. Beyond the capillary length, which is smaller than 2.5 millimeters for most liquids, gravity dominates and flattens the droplet. This is why when we spill a cup of coffee on a table, we end up with a puddle instead of a huge spherical coffee lens. In order to overcome gravity, we create our fluidic lenses inside an aquarium filled with an immiscible immersion liquid. By matching the density of the immersion liquid to that of the optical liquid, we create a microgravity environment where gravity is fully counteracted by buoyancy. Here you can see a video demonstrating manual injection of a simple 1-inch symmetric spherical lens. The curvature of the resulting lens is dictated by the injected volume. Adding more volume will increase the lens's curvature, while removing volume will decrease it. If the volume of the lens is taken to be smaller than the internal volume of the cylindrical bounding frame, then the optical liquid will form a concave lens with negative curvature. This brings us to the second problem, the second obstacle of making fluidic lenses, that is the shape of the lens. Obviously, we don't want to make actual droplets, but rather lenses, and preferably with more interesting shapes than just symmetrically spherical. There are two main parameters that allow us to control and vary the shape of the lens. The first one is again the density difference, which we can vary near its neutral buoyancy value. And the second one is the geometry of the bounding frame. So let's see what it looks like theoretically. We start with a simple model where an optical liquid is injected into a ring-shaped bounding frame, surrounded by an immersion liquid. In this system, the capillary length is inversely proportional to the density difference between the immersion liquid and the optical liquid, so that if the two densities are matched, the capillary length goes to infinity and gravitational effects disappear. Here there's an additional component to the setup. You can imagine that the bounding frame is sitting on top of a transparent cylinder marked in the image by black lines. When the liquid lens is formed, it encloses the immersion liquid inside this cylinder, separating it from the outer volume. Adding or removing immersion liquid from this enclosed volume allows us to inflate or deflate the liquid lens, as we will see later on. We are interested in finding the shape of the top and bottom interfaces, h-top and h-bottom. Since the system is at a steady state equilibrium, a natural approach is to use the energy method. The functional F defined here represents the free energy of the system, and the steady state is achieved at the minimum of this functional. The first two terms under the integral sign are the contribution from the interfacial energy, one from the top surface and another one from the bottom one. The third term is the contribution from the gravitational energy, so that at neutral buoyancy this term disappears. The last two terms represent the geometric constraints. One constraint is the volume of the lens, and the other is the enclosed volume I mentioned previously. Minimization of the energy functional results in the standard Euler-Lagrange equations for the top and bottom interfaces. If we look at the equations, we'll see that under neutral buoyancy conditions, when delta rho is equal to 0, the equations collapse to the well-known Young-Laplace equation. Divided by r, the term on the right represents the mean curvature of the interface. Therefore, under neutral buoyancy, the solutions to these equations are constant mean curvature surfaces, where the specific type of surface is determined from the shape of the bounding frame. For example, a simple cylindrical bounding frame will result in a spherical lens, the curvature of which, whether positive or negative, is dictated by the injected volume, as we previously described. In the picture, you can see some simple comparison between the theoretical solutions to the governing equations and the corresponding neutral buoyancy experiments. We can easily break the up-down symmetry of the fluidic lens by adding or removing liquid from the enclosed volume, thus effectively inflating or deflating the lens. This allows us to create meniscus lenses, which are widely used in corrective eyewear, as well as in many other applications. After the desired shape is achieved, the optical liquid can be cured to produce solid components. Here are some examples of solid lenses created under neutral buoyancy conditions in our lab. The simplest are, of course, spherical lenses, like the 1.5-inch lens you can see here. We can make convex lenses, like this thick variant with high curvature, and we can make concave lenses, like the examples on the right. One of these lenses is a symmetric concave lens, here dyed in red for better visualization, and the other two are cross-sections of a meniscus lens. In the bottom row, you can see some examples of more complicated lenses, made by the same method. The first is a cylindrical lens, which is created using a specially designed bounding frame. Next is a bifocal lens. This one is created via a two-step process, where a plano-convex lens was first made, then cut in half, and used as part of a bounding frame for another plano-convex lens with a different curvature. Here you can see a saddle lens, also known as a toroidal lens, which has negative curvature along one axis and positive curvature along the perpendicular axis. This lens is made in a way similar to the cylindrical lens, but with a different volume of the optical liquid. Lastly, you can see a doublet lens, where a concave lens was first created and then used as a bounding frame for a convex lens made out of another polymer with a different refractive index. Here, the other polymer is dyed blue for visualization. An important aspect of the fluidic shaping method is that due to the natural smoothness of liquid interfaces, the solidified lenses are of excellent surface quality and do not require any polishing whatsoever. Our atomic force microscopy measurements yield surface roughness on the order of 1 nanometer RMS. The picture on the right was taken during an actual demonstration of the fluidic shaping method, where a 1-inch lens was created from fluid injection to solidification in under 10 minutes. As you can see, the fabrication does not require cleanroom facilities, yet the resulting surface quality is on par with the best technologies out there. Everything I showed you until now was done under neutral buoyancy conditions. However, if we allow the density difference to deviate slightly from zero, even more interesting shapes can be obtained. We can non-dimensionalize the governing equations, introducing a small parameter, epsilon, into the problem. This parameter represents the ratio of the vertical characteristic length, for example, the height of the deformation, to the horizontal characteristic length, which could be the radius or the diameter of the lens. At the leading order in epsilon, the governing equations for the top and bottom surfaces turn into Bessel and modified Bessel equations, respectively. The governing parameter here is the bond number, which is just the dimensionless version of the inverse capillary length. These equations are solvable exactly, and the solutions are simply the Bessel and the modified Bessel functions. On the right, you can see how increasing the bond number allows us to deviate from a spherical shape and obtain an aspheric lens. We can also fix the bond number at some non-zero value, and by varying the lens's volume, we can obtain other interesting shapes, like the one in the bottom simulation that resembles slightly the Schmidt corrector plate. It is important to note that even though at non-zero values of the bond number, the liquid lens is not at neutral buoyancy, the effect of gravity is still very small and the liquid lens remains stable. Here you can see a liquid bezel lens, 9 centimeters in diameter, so this is not a small lens, as it is being forcefully disturbed by steering the immersion liquid. Once the steering stops, the lens relaxes back to its bezel shape. Comparing our theoretical model to experiments yields excellent agreement without any fitting parameters. The blue and red curves in the image represent the theoretical top and bottom interfaces, and all the values used in the model were measured directly from experiment. Another important property of the fluidic shaping method is its scale invariance. In the case of neutral buoyancy, the capillary length goes to infinity, eliminating any effect of gravity and resulting in scale invariance. This is evident in the picture on the right, where you can see a 200 millimeter spherical telescope lens fabricated using the fluidic shaping method. But this scale invariance remains true also for the aspheric case, since the shape of the lens is determined by the dimensionless bond number, which in itself is a function of the lens's diameter and the density difference. So that for any diameter, we can adjust the density difference to yield any desired bond number. The most interesting results are obtained when we allow the bounding frame to have non-axisymmetric configurations. Then, the same variational approach yields a more general partial differential equation governing the shape of the fluidic interface. Here, for simplicity, we consider only the top surface. We can again linearize this equation to obtain a much simpler one, with the boundary conditions now being a general function f of theta that represents the varying height of the bounding frame. The linearized equation is separable, and we can solve it exactly through a polar bezel expansion, where the expansion coefficients can be determined from the Fourier coefficients of the boundary functions. In other words, giving the values of the bond number and the volume constraints, the known function f of theta dictates the topography of the resulting optical surface. Here you can see some basic modes of the general solution. Each row corresponds to a specific mode number, and each diagonal corresponds to a specific bond number. Different combinations of these modes can produce various free-form optical components, while maintaining all the benefits of the fluidic shaping method, namely the scale invariance and the excellent surface quality. It is important to note that not all of these modes can be superposed on one another, since it would require having several different values of the bond number in the same setup. That said, there is still an infinite number of producible surfaces for any given value of the bond number. Here is one example of a simple freeform component that we designed and fabricated using the fluidic shaping approach. This component is designed to optically square the circle, as shown in images C and D. The bounding frame in this example was 3D printed, and the polymer used to create the component is just standard PDMS. I would like to note that this method does not depend on any specific optical liquid. We used a wide range of different polymers, both photocurable and thermally set ones. In principle, any curable liquid can be compatible with the fluidic shaping method, as long as the appropriate immersion liquid can be identified. So, what's next? In this picture, you can see what is, at least to the best of our knowledge, the largest lens in the world right now. This lens was made for the Large Synoptic Survey Telescope. It's 157 centimeters in diameter, and it took several years and almost $20 million to make. The fluidic shaping method could potentially be used to produce even larger lenses for a fraction of that price. Another potential application has to do with the question of how to increase the capillary length. One way of doing so, as we've seen until now, is by decreasing the density difference in the denominator here. But an alternative way is to simply get rid of gravity. In orbit, the fluidic shaping method can be used without any immersion liquid in order to create extremely large fluidic lenses. These lenses can be solidified, or they can be left in their fluidic state, allowing for dynamic control of their focal length. We are currently collaborating with NASA's Ames Research Center to test this technology under microgravity conditions in a series of parabolic flight experiments planned for early May this year. We're also collaborating with researchers from NASA's Goddard Flight Center, who developed a method that allows to quickly apply reflective coatings using atomic layer deposition techniques. The idea behind the latter experiment is to produce a concave lens during a microgravity parabola, and then to coat it in a subsequent parabola, creating a spherical mirror in microgravity. Another interesting aspect of the fluidic shaping method is that it may allow simple and rapid fabrication of optical components in space. For example, on board of the International Space Station. We are currently working on a device which will allow to quickly fabricate optical components in space in a way analogous to 3D printing. Some of these components might be extremely difficult, if not impossible, to produce on Earth. Thus, the fluidic shaping method may contribute to future space-based economy. Finally, I would like to acknowledge the fantastic group of people that is responsible for this project. First and foremost, Moran Bercovici, who heads the Microfluidics Technologies Laboratory at Technion and is the driving force behind this project. Elgarisi, who is advancing the freeform part of the fluidic shaping method, and Omer Luria, who is leading the NASA collaboration project on the parabolic flight experiments. This work would not be possible without their help and contribution. Thank you very much for your attention, and we'll be very happy to answer any questions.